Hey guys, so in this video I will be going over the false position method, which essentially uses a straight line to estimate the root location of our function. So let's go ahead and get started. This is our given function with our given bounds, and we are told that our error tolerance for our estimate needs to be less than 10%. So the first thing we're going to do is graph the function. And I have already done that here in MATLAB for you so that it's nice and pretty. The next thing we're going to want to do is perform our first iteration, which I'm actually going to continue on the next page. So the first step of our iteration is to determine the x lower, x upper, and the function value at each of these bounds. So these conditions were given to us as 0.5 and 1.5. And then we simply take and substitute these values into our function. And we get negative 4.5 and 12. The next step is to calculate the root estimate for this iteration. And we're going to use this equation that I've boxed in blue and have expanded on down here. So XR is the estimated root location, XU is the upper bound, XL is the lower bound for our iteration, and then we need to find the function value at each of these locations. So using the information that I've defined up here, I'm simply going to take and substitute these values into that function and get my root estimate. So XR1 equals 1.5 minus the quantity of 12 times 0.5 minus 1.5 divided by negative 4.5 minus 12. And that calculation gives me 0.77273. The next thing I'm going to want to do is calculate the function value at this root estimate. So I'm simply going to take x of r1 and substitute it into the function that we were given. And that gives me negative 2.09166. Step D is to calculate the product of the function value at the lower bound and the function value at the root estimate. Multiplying those two terms together, I get 9.41247. And this term is important because it will tell us which section of our bracket the actual root of the function is in. So if we look down here at the red box, we can have two different cases. For the first case, if this product is less than 0, that means the function signs are opposite. So one is positive, one is negative, and therefore the actual root is in the lower section. And so if we need to perform another iteration, we would set x upper of our next iteration equal to the xr that we just calculated, and we would keep the lower bound the same. The other case we can have is if the product is greater than 0. And in this case, the function signs are the same, so they're either both positive or both negative, and therefore the actual root is in the upper section. And so, if we need to perform another iteration, we would set the lower bound equal to our root estimate, and we would keep the upper bound the same. So in this case, our product is greater than 0. So that means we have a case 2 situation. And that tells us that if we need to perform a second iteration, our lower bound for that iteration would be equal to XR1, which is 0.77273, and our upper bound will stay, that's supposed to be an X. Our upper bound will stay the same. The last thing we're going to want to do for this iteration is calculate the error. And I have expanded on this formula down here in purple. So I'm using percent relative magnitude approximate error because I'm not given the actual root location. So in order to calculate my error, I'm going to compare my previous iteration value to my current iteration value. So in this case, our current iteration value is 0.77273, and our previous is 0 since we don't have a previous iteration. And that will give us a 100% error, which actually should make sense because this is our first iteration, and so we don't have anything to compare our estimate to. So since 100% is greater than the 10% error that we need to be under, we will need to perform a second iteration. But before we do that, I'm going to go back to this graph, and I'm going to show you graphically what we just calculated. So I'm going to pick red to represent iteration 1. This is my lower bound, and this is my upper bound. And so if you recall, the false position method uses a straight line to approximate the function and looks at the x-intercept of that straight line for our root estimate. So I'm going to mark the function value at our bounds. And unfortunately, this one is going to be off the graph, but that's okay. And then I'm going to use a straight edge and connect these two points with a straight line. This is going to be difficult. It's a lot easier on a piece of paper, I promise. It's close enough. You get the idea. Alright, so here's our straight line. And the x-intercept of the straight line is right here, which is the XR value that we calculated. And that looks like it could be about 0.77. So it looks like we're on the right track. And then we determined that the actual root is in the upper section. And so we got rid of the lower section, which is right here. All right. So now I'm going to move on to the second iteration. And the first thing we're going to do is identify our lower bound, upper bound, and the function value at both of those locations. So, it should be a 2. So our lower bound was 0.77273, and our upper bound was 1.5. And then we have the function values at these locations. And so we have negative 2.09166 and 12. Our next step is to calculate our root estimate for this iteration. So XR2 is 1.5 minus the quantity 12 times 0.77273 minus 1.5. And all of that is divided by negative 2.09166 minus 12. And that gives us a root estimate of 0.88068. Step C is to calculate the function value at this estimate. And I got that that was negative 0.75590. And then step D is to calculate the product term. And I got that that was 1.58109. So this product is greater than 0. And so going back to our conditions down here, this means that this is also a case 2 situation. So therefore, if we need to perform another iteration, we will set the lower bound equal to the root estimate, and upper bound will stay the same. So let's see. This was a case 2 situation. And that guy's going to stay the same. All right. So the last thing we need to do is calculate the error for this iteration. So our current root estimate is 0.88068. And this time we do have a previous root estimate, and that was 0.77273. And we're going to divide by our current estimate, 0.88068, and multiply by 100. That will give us 12.26%. So this error is less than the 100% that we had on our first iteration, but it's still greater than 10% error. So we will need to perform a third iteration. And again, before we do that, I'm going to go graph this iteration so that you can see what we just did. Graphing your work, I will say, is also a really great way to check for mistakes, especially if you're really super stressed, like on an exam. So I know it's a little tedious, but I would highly recommend doing this every time. All right, so there are my function points. And I'm going to use a straight edge, aka a Deadpool DVD, to connect these dots. Looks close enough. All right. Okay. So our root estimate is right here, where this line crosses the x-axis. Let's write it right here. And then we determined that the actual root is in the upper section. And so we got rid of this little section right here. All right, so it looks like we are on the right track. So I'm going to move on to my third iteration. And again, I'm going to define my bounds and their function values. See, I got that this guy was negative 0.75590. Okay. Step B is to calculate XR. And so that's going to be 1.5 minus the quantity 12 times 0.88068 minus 1.5, all divided by negative 0.75590 minus 12. And that will give me 0.91738. And then I'm going to calculate that corresponding function value. I get negative 0.24796. Step D is to calculate the product term. So the function value of our lower bound times the function value of our root. And that gives me 0.18743. And this term is greater than 0. So that means that we have a case 2 situation. Therefore, if we need to perform another iteration, our lower bound will be equal to this root estimate, which is 0.91738, and our upper bound will stay the same. All right, and then the last thing we need to do is calculate the error. So our current root estimate is 0.91738, and our previous root estimate is 0.88068. We're going to divide that by 0.91738 and multiply by 100. And that will give us a 4% error, which that is less than the 10% error that we needed to be under. So therefore, the answer to this problem is that our root estimate is this 0.91738. So the last thing I'm going to do is graph our iteration. So this is the upper bound. This was our lower. And again, I'm going to connect those with a straight line. Like that. Okay. And our x-intercept of that line is right here. And as you can see, it's almost on top of the actual root of the function. So graphically, what we've just done makes logical sense. And so that's it. I hope this video helped you guys better understand the false position method.